Hello and welcome back. The subject of this video will be to work a couple of problems to apply these concepts of torque that we've looked at in the previous two videos. Just to remind you of the definition of torque, torque is equal to R cross F. Remember, this is the vector or cross product. It has a very specific way to find the magnitude part of it and a very specific way to find the direction part of it. The vector R is the vector that points from the axes of rotation to the point of application of the force. The units for torque are going to be the units for R, which are meters, times the units for force, which are newtons. Meter, newton. Now you're going to recognize the combination of a meter and a newton as a joule, but we do not refer to torque in units of joules. We will keep it as a meter, newton. And I'll keep the meter in front to remind us not to combine those two into a joule. Different unit than the unit for energy. There's a radian that is missing here between the units for torque and the units for energy or work. And remember that that radian's the funky unit that kind of morphs in and morphs out. So anyway, let's go ahead and apply these concepts of torque to a couple of problems. The two problems that we're going to look at are both from the OpenStax text, 9.1 and 9.2. So 9.1 reads as the following. When opening a door, you push on it perpendicularly with a force of 55.0 newtons at a distance of 0.850 meters from the hinges. What torque are you exerting relative to the hinges? Question mark. And B, does it matter if you push at the same height as the hinges? So we know that the force that we're going to be exerting is going to have a magnitude of 55.0 newtons. And we also know that it's going to be at a distance of 0.850 meters from the axes of rotation, i.e. the hinges, i.e. where we're going to sum the torque about. So, or not sum the torque about, but calculate the torque about. So now in part A, we want to know what is the torque. So for A, the torque is equal to question mark. And then in part B, does height matter? So these are the two questions we're off to answer. So first of all, I'm going to just draw a picture of this door. And here are the hinges. So again, those are hinges. And notice that the axis of rotation of the door goes right through the hinges. And we're going to be applying a force of 55 newtons. They tell us perpendicularly. So let's pretend that we're actually applying that force into the board. Okay, so this is going to be the force's direction, F. And we want to apply, we want to now draw the vector R. So R goes from the axis of rotation to the point of application of the force. So there's R. We want to calculate the torque. So let's draw R and F over here separately. So R is in this direction, and F is into the board. And now we want to know what is the torque's direction first. And notice that I could have had F out of the board, into the board. Either one, your drawing should correspond to the correct direction for the resultant torque. So you may have this as a force out of the board, and that's totally fine as long as your direction of the torque aligns with your chosen direction for the force. So practicing the direction part of the torque, remember my right hand goes into the direction of the first vector, which is R. So my right hand straightened in the direction of the first vector, and now I want to be able to bend my right fingers in the direction of the second vector, which is F. And that's into the board. So my palm needs to be facing into the board. Then my fingers can bend into the board. Notice my thumb extended now is straight up, and that is the direction of the resultant torque. So now we know the direction part of the torque. The direction part of the torque is up. What about the magnitude part of the torque? Well, remember the magnitude part of the torque comes from the magnitude of the first vector, magnitude of the second vector, times the sine of the angle in between the two vectors. So what is theta for this particular case? Well, R and F are at 90-degree angles to one another. So theta is equal to 90 degrees in this case. So we can calculate the torque then immediately. The magnitude part, we already have those quantities defined. So the magnitude of R is 0.850 meters. The magnitude of F is 55.0 newtons times the sine of 90 degrees. The sine of 90 degrees is 1. And so we're going to have 0.85 times 55 times 1. And so the torque is going to be equal to 46.75 meter newtons. And so now I'm going to express the torque as a vector, and I'm going to use our standard coordinate system. And that standard coordinate system is going to be that y is up, x is to the right, positive y is up, positive x is to the right, and out of the board is the z direction. And notice that this little coordinate system also follows the right-hand rule in that x crossed into y gives me a positive z. That must be adhered to for a right-hand coordinate system. So x crossed into y must give you z's direction. I'm using the unit vectors that we got introduced to earlier in the semester. So we can see that the resultant torque does lie in the y direction. So writing the torque as a vector with the correct number of figs, 3 being the correct number here, I can write the torque then as 46.8 meter newtons in the positive y direction. So there is the answer to part A. The magnitude of the torque exerted by this force that we exert a certain distance from the axes of rotation is this magnitude and this direction. In part B, does it matter what height we apply that force at? So what if instead I decided to apply the force down lower, let's say maybe, let me see if I can find a pen that's a different color. What if we applied the force down here instead? Or what if we applied the force up here instead? Notice that those vectors R would still be the exact same magnitude and direction. So the direction part of the torque would not be affected by moving the force up and down a vertical height. And the magnitude part of the torque also would not be affected, as the magnitude of R and the magnitude of F and the angle between the two also would not be changing. So it does not matter where I apply the force, as long as I'm still the same distance from the axes of rotation, as long as I still apply the same magnitude of force and it is in the same direction, then the magnitude of the torque and the direction of the torque will be the same. So does height matter? The answer is no. Height does not matter. Okay, so we have completed then 9.1. Let's do 9.2 now. It reads, when tightening a bolt, you push perpendicularly on a wrench with a force of 165 newtons at a distance of 0.140 meters from the center of the bolt. A, how much torque are you exerting in Newton meters relative to the center of the bolt? Notice we're always being given where we're calculating the torque relative to. So part A, how much torque are you exerting? And then in part B, convert this torque to foot-pounds. If you look in your textbook for conversion ratios, you're going to find that 0.738 feet-pounds are the same as 1.0 meter newton. So this is going to be the conversion ratio we're going to need for part B. So in part A, we're asked to find the torque being exerted by this force. So the force is going to be 165 newtons, and the distance we're applying it from the center of the bolt, where we are summing the torque about, is going to be 1.40 meters. So in A, what is the torque? Torque equals question mark. And then B, we want to know the torque in feet-pounds. So that's just going to be a unit conversion once we get part A. Okay, so let's go ahead and draw a picture of what's going on. So we have a bolt, and I know it's got straight edges that make up a hexagon, but we're just going to draw it as a circle for these purposes. And we have the center of the bolt right here. So this is our bolt, and here's the center of the bolt. And we are exerting a force that is perpendicular to the bolt itself. So we're going to be exerting a force that looks like that. So there's the direction of the force. The vector r goes from where we are calculating the torque about, that is the axis of rotation in this case, right? The bolt is going to be rotating about this point to the point of application of the force. So there is our vector r. Okay, so notice for this case, r crossed into F gives me a torque into the board. Into the board gets the cross symbol, and into the board is going to be in the minus z direction. So we can draw r and F out here to the side. Here's vector r, and here's vector F. And so then the resultant torque is into the board. So that's the direction of the torque. The torque is going to be in the minus z hat direction. So let's go ahead now and calculate the magnitude part of the torque. So the magnitude part of the torque is going to be the magnitude of the first vector, which is r, times the magnitude of the second vector, which is F, times the sine of the angle between r and F. The angle between r and F is 90 degrees. So theta is equal to 90 degrees. We're told that the force is being applied perpendicular to the bolt. So that means it makes a 90-degree angle with respect to our vector r that goes from the center of the bolt to the point of application of the force. So we have these quantities defined over here. So again, this is just plugging in. Torque is equal to r, which is 0.140 meters, times F, which is 165 newtons, times the sine of 90 degrees. Sine of 90 degrees again is 1. So we come up then with a magnitude of the torque of 23.1 meter newtons. Okay, so this is a 3-fig problem. This is 23.10000. So this is how I would express my answer in 3 figs. And I can write it then in full form with respect to how I drew it. This is in the minus z hat direction. So this is going to be 23.1 meter newtons minus z hat. So it's in the minus z hat direction. In part B now, so that was part A. In part B now, we just want to convert the units. So the direction part doesn't change just because we're putting the torque in different units. These are the British units for torque. So let's go ahead and use this ratio that we can flip back and forth between the units. Remember that when we divide both sides by either of these, we form a ratio whose value is 1. So in part B, we want the torque in feet-pounds. We currently have it in meter newtons. So let's take our torque, which is 23.1 meter newtons, and now let's multiply it by a ratio. Which one do I want in the denominator? Well, I want to get rid of the meter newtons that's in the numerator, so I want that 1.0 meter newtons in the denominator, and then I want the 0.738 feet-pounds in the numerator. So the meter newtons cancels, and when I take the 23.1 and I multiply it by the 0.738, I come up with 17.0. So the torque can be written in the British system as 17.0 feet-pounds in the minus z direction. Your direction may be different than mine. I drew my bolt in the plane of the board, that made F and R both lie in the plane of the board. And so because of the direction I chose F, I could have chosen F downward. If I had chosen F downward, then R cross F would have given me a torque that is pointing out of the board instead. That would have been the positive Z direction. But notice that my drawings and my resultant answer all correspond, and that's what's important for you. You can draw these in any direction, but your results must tie into what you have drawn and what you have assumed for directions. So this gives you an idea of how to apply to a couple of problems from the text. In the next video, we'll talk about equilibrium, the conditions to satisfy static equilibrium, and then we will work on some problems from the text in that area as well. So we'll see you next time.